Hi, this is the presentation of my master thesis, Curiosity-Based Self-Organization of Humanoid Robots. In this work, I made a humanoid robot teach itself from scratch how to do basic things such as rolling around or to sit up.
Alright, we will begin with the background, where I will talk shortly about why one would want self-organizing robots, and also a little bit about reinforcement learning, which is the main method I have been using to accomplish this. And then I will talk about my method, how I developed it, and what the key components are. And then we will see some results and some conclusions, and then there will be questions, and my opponent will be able to ask some questions. Alright, background. So, why self-organizing robots? Two very important things is that if you have a robot that is able to learn itself, you don't have to program the robot specifically. And it's really good if you have a slightly different robots, then you don't have to program each robot individually, but each robot is able to make sense of their own bodies. The next thing is that even if you have a robot that is well programmed and it might be able to walk pretty well, then something might break down. For example, it might some joint may become more stiff or something like that, and then it's really useful if the robot is able to sense that something is wrong here and then correct its behavior to better suit how its body works then. There are a couple of different ways you can accomplish this. This is just a few of them that I looked at. I will only talk about reinforcement now because that's the method I used. So what is reinforcement learning? In its core, it is about knowing what to do in a certain when you're in a certain position in order to get some reward. For example, a state could be, are there or are there no cookies? And if there are cookies, then you can choose different actions. For example, if there are cookies, you can make the action to try to eat them. And then if you eat them, then there could be a reward. You can like the cookies or not. And the thing here is that the robot is able to learn that if there are cookies and you ate them, then you had a positive experience, and that makes it more probable for the robot to try to do that in the future. So the robot will do the things that it gets a positive feedback from. More specifically, when one implements reinforcement learning, one could have a state space, in this case a chessboard, and then you have an agent, a horse in this case, and the horse could be, in this case, in almost any state here. And then there is an action space of the things that the horse could do, the knight could do, and that's the crosses. And you can see that it can't do all action. It can't go to all states in actions. So there's a limited amount of actions in this case. Then you have probabilities that might be not suitable for chess, but in reality it could be that if you try to do this action to go here, then there might be a chance that you fail. For example, if you try to eat those cookies, there's a 50% chance that your mom will stop you. And also there are rewards for, how much did you get from this? You could also have negative rewards, that you get punished in some way for doing it. And the reinforcement learner doesn't know in advance what those probabilities look like or what those rewards look like. So it's up to the agent to, while it's running, to figure out how does this look. Alright, when you implement a reinforcement learner, at least in my case, these are two very important questions. And that is, how do we define a state? And also, what is the motivation? What do we want to reward the robot for? What kind of behavior do we want it to learn? Typically, when I have been looking at other studies, an answer to what is a state, it has been, they try to capture almost any possible posture of the robot. And the problem with this is that a robot could have a lot of different postures. If you only have one arm, then you perhaps only have these postures, but if you have as many joints as a human has, then it's inconceivable. And as a motivation, a typical measure is to just measure perhaps how much did the robot travel forward when doing an action. And the problem with such a measure is that it can't do much else basically, when it has learned to do those things. All right, so how did I implement this on my robots? Let's begin to look at my robots and see what it looks like. Meet Bob, my Bioloid premium robot, sitting over there right now. He has 18 servos, and if we would do the classical implementation of trying to capture all the possible postures it could have, let's say we just allowed each servo, each joint, to just have 2 different settings. If we would do that with 18 servos, we would have 260,000 states. And to be able to train a robot to find which of those states are the better ones, it just takes too much time. So it can't really be done. When other people have been doing this, they have like told the robot that they can only move symmetrically, or that each leg, each arm is their own agent. So I haven't seen anything where someone has used more than perhaps 6 dimensions, and this is 18 dimensions. And then we have a 2D accelerometer, and what it tells us is basically what is the tilt of the upper body of the robot, so we can feel what is this angle here. All right, so let's go back to the questions. What is the state and what is the motivation? Let's start with what the state is. What I have done is to basically break down the state space in 2 parts. First of all, we have direct coordinates. We'll look at the features that the robot is in immediate control over. In this case, the robot is in immediate control over the angles of every servo. It could be other stuff, like do the robot want to make a sound or something like that. But in this case, we only have these angles. And that means that we can make a vector here with all those, which is x. And in this case, since we only have different angles, then each x will correspond to a unique posture of the robot. And notice that any posture is possible. This is continuous. We could have any at all. And then we have the global coordinates, which are the coordinates, which is the features that the robot isn't in direct control over, but often is able to affect in some way. In this case, the tilt of the body. So it can't decide, I want this tilt and just get it. But it is able to affect the tilt of the body by using its servos. Let's look a little closer at the different positions. Since we're able to make each posture to a vector, then we can also do basic algebra. So perhaps if we have this posture and this posture, then we can take the mean out of them and get a posture right in between. So this way we don't have to worry really about the dimensionality of the robot, since we reduce them to a vector. All right, so how do we use these 2 things to be able to do a reinforcement learning with a robot? What we basically do is that we just keep the global space, the different tilts of the body, and make a state space out of that. So within this square, we have some unique tilt. Here you can see this from the side. So for example, this is if the robot is standing here in the middle and tilting its head over here. So then we say that if the robot is tilting within this square that is defined by this tilt, then you are in this state. And our task is to try to find a posture for the robot that will support it while in this state. So basically, from 260,000 states, we're down to 25 states now, which is a lot lesser state space to look through. So, in other words, every state corresponds to a unique tilt. And we should find one posture that is stable in that state. So how do we find these postures? Well, we have a couple of different options. First of all, notice that regardless of the posture of the robot, it will always be in some state. It will always have some angle on the body. So because of that, for some states we will have previous experiences of how it is to be in that state. For example, let's say we have 2 examples of one state. We're lying on the back. We're lying on the back, well, like this, and perfectly in this case as well. So what I then do is that I take the mean out of it to try to find the essence of that state, somewhere in between that state. But we have another option, another case too. What if we have never seen that state before? What if we try to figure out how to move the body and able to reach some state that we haven't seen before? So let's say, for example, that this is the posture of having a 10 degrees angle. This is the posture of having 20 degrees angle. And now we're searching for 30 degrees angle. We have never seen that. So where should we look? So our first guess is to just use the linear guess and guess that since these two are related in this way, then a good way to start look is around here. Beside this, we have another feature too, and that is how certain we are. So we have an approximation of where to look for a state, but we might have a very low certainty level, and that means that even though we think that this is a good place to look, if we have never seen this before, we should look in the whole area around here to do some exploration. But let's say we have seen a state a couple of times, then perhaps we should narrow down our search area a little bit. So what is the motivation of the robot? In this case, I have been using something called curiosity-driven learning, and it is basically to try to optimize the learning process. And this is extremely simplified, but I just want to give you a feeling of what it does. So let's say that the robot is in this state here in the middle, and it has tried all these transitions a lot of times. So the green transitions has been tried a lot of times, and they have always succeeded, and the red ones has never succeeded, but the yellow ones have changed in their odds of success or failure. And this tells the robot something. It tells it that we are starting to find good postures here. Something is being learned here. So what I basically tell the robot is to keep track of its previous record of how it's supposed to work, and try to see where it is improving the most. So the robot always tries to do the actions that will improve its understanding of how to move around in its state space the most. And a final feature that I added is that when it has learned how to move around here, you could basically start to control the robot and say that go here. And if it's here, then it could follow just the green actions to see how can I go to this state in the most safe way. So yeah, basically the robot is learning how to control the global parameters with its direct coordinates. Let's look at the results. I've done 5 different experiments, and we don't have the time to talk about all of them now, so I will just tell you about 2 of them. So in this experiment, I wanted to see if the robot was able to notice a difference in its morphology, if it would be able to notice that something was wrong, so when something changed with the body. So I trained a robot with 2 arms, and then I removed 1 arm, and I wanted to see, was it able to notice that it didn't work anymore to roll over on the side without an arm? Would it be able to correct its behavior? And what basically happened was that the robot noticed that the postures it had been using previously didn't work anymore, and that meant that its certainty level became less, so it expanded its search area, and after a while it started to find new states that worked better. So in that way it was able to correct its behavior, and soon it moved actually better than with 2 arms, because it's easier to roll over without an arm there that might mess things up. Also notice that this robot has actually 3 servos less. And I didn't have to do anything about it. I didn't have to change the state space or anything, because all the servos was just in this vector. But in a classical implementation, you would have a whole different state space, because the state space was defined by the numbers of servos. In this experiment, that we will look at a little bit closer, the robot had a state space of 7 times 7 states. And so this is the state space of the robot after 200 iterations. And the brighter colors means that it has a higher certainty. So up here, you see, these are positions when the robot is lying on its back. So you see, after 200 iterations, it knows how to be on your back, but not much else. Over here, after 500 iterations, it starts to find out how to be on this side. And here it finds out the belly. And over here you can see that it starts to figure out how to be sitting up. And it also had an action radius of 2, and that means that it was able to do any action where it went to some other state that was 2 or less neighbors away from it. So let's have a look at its training. So this is iteration 0. It is newborn. It knows nothing of what it looks like. So we just do random actions, basically. And every time it moves is 1 iteration. So let's say now it has a good concept of lying on its back, but it don't know how to move its body to get to some side. But here, by an accident, it finds out a side state, so it will remember that. So the next time it wants to go there, it will use that posture again, but it will do something around that because it has a search area. Starts to realize how to do some basic transitions from the back. A whole new world. The robot has found belly, what it is like, and it's really, really exciting for the robot because it has no concept of what being on the belly means. And it's a little hard for it because you can see it intertwines its legs. We will come back to that later, actually. I can add that the robot hasn't been on the belly all the time these last 500 iterations. It has been doing different stuff, but now it's back on the back again. And the transition between being on your belly, you see there, and going to your side is a pretty difficult one for the robot. And remember that it was able to go from the belly to its side now, because that is something that will change, and I will talk about that later. After 2,000 iterations, this is about 2 hours of training, perhaps. It might look a little clumsy, but that is because it always tries to do the things that is challenging for it. It doesn't try to do the things that it already knows how to do, because it wants to improve the most. So you will often see that it do things that doesn't look very skilled. All right, that is 3 hours of free play. So now let's test the robot and see what it has learned by doing this. Can everyone see? There will be text down here I'm telling the robot what to do. So go to your left side. Can everyone see that? Mm-hmm. the robot wasn't able to go back to its back, even though we have previously seen that it was able to in fact go from the belly to the side. So somehow it has lost this ability, and it was not because of these cables, I can assure that. So what happened here? If you look here, we can see that it knows here of the 2000 iterations how to go between here, but something happens here and it loses its certainty. So what I think has happened is that there is conflict over here, because these states are good for two things. You can either use them as a transition from the side to the belly, or you could use them as a transition from the side to sitting up. And the problem is that the postures in these angles, in these tilts that are beneficial for going to the belly, are not the posture that are good for sitting up. So what happens is that since I take the mean, we will have some state that is somewhere in between, meaning that you will have some postures there that are actually good for nothing, and the robot can't sort it out. It can't find a posture that is good for both. All right, so what are my conclusions? First of all, this method enables a high-dimensional robot to operate efficiently within a smaller sensor space. The robot can adapt to changes in its morphology. It is able to cope with a lost arm. And finally, the robot is able to learn the basic skills within hours. So we have a rapid learning curve for the robot in real time. That is my presentation.
So in this case, it's first it does something and then it pauses for a
Yes.
second or something. Have you tried without that? And how would that work?
The reason for the pause you can see between each iteration is that the accelerometer in it measures the gravitational force. And for me to have a good measure of that, it's important that that there are no other forces acting on the robot when that happens. So in the beginning I had at least shorter pauses, but then it often guessed wrong and it confused and didn't know what posture should I have in what state. So yeah, I have tried shorter pauses, but it's better to have longer ones. Perhaps you could, when you test the robot, perhaps you could have something that you allow it to do 2 actions in a row if it has certain certainty of succeeding, so that it just assumes that it goes where it wants. But yeah, that's future work, I guess.
Yeah.
What were your own expectations as to how it would be able to move after a few hours? Were you surprised by its capabilities, or?
I had, if everything worked as I intended, it should be able to learn these things. But I didn't really know to what extent it would be able to do more complicated stuff when I only allowed 1 posture for every state, because I didn't have very many states. So I'm a little impressed that few states were able to be so useful to it. For example, as we could see, 1 state perhaps didn't suffice when it was able to go both to the belly and both sitting up. But I was actually impressed that the states that I gave it permission to use, that they were so useful. And but yeah, it was really good that it was able to train so fast. But it was important for my work that it was, because I wanted to implement this on a real robot that were interacting just with reality. I didn't want to use simulations or something like that.
Would your method work with, for example, a robot that has several methods of input? For example, if it has 3 or more accelerometers within its body on different positions, would
Yes.
it be able to cope with this?
Yes, it would. I actually added 1 global parameter. I added in 1 experiment, I allowed it to feel how stretched out its legs were. So it had 3 states. 1 to feel the legs were stretched out, 1 if it was like here, and 1 if it was like here. And what I wanted to see was basically, I wanted to give it a state where it was forced to be standing up. Because if the legs are stretched out and its body's pointing right up, then it must be standing up. So I wanted to see that, but it wasn't. It was too complicated for it, but it was still able to navigate within that space. But yeah, you could. This method is really general. You could use it on any kind of robot. You could build your own Lego robot and implement this, and the robot would find out by itself how to go around in its global state space. The problem is if you add more dimensions to the sensor space, is that you get more states for it, so the search will be longer. But yeah, the method is very general. You could actually implement this on your speakers, and if you allow it to measure how much a wine glass is vibrating, it would by itself figure out what frequencies to play in order to make the glass vibrate. So that's a whole other thing you could use it for, if you would like that.
Have you done any benchmarks against other methodologies, or on any research papers saying, what's the benefits of one against the other? I mean, your approach.
Yes.
To teach or to ensure that the robot is learning in the right manner.
Yeah.
Have you done any benchmarks, comparisons to other methods to see, is this approach being used widely in the private businesses? Or,
No, I made this method myself, and when I have been looking at different studies before, then when people have been trying, at least in the work I have seen, when people tried to make robots, at least humanoid robots, use reinforcement learning, one example is that they had a simulated robot, and they for example, enforced it to have a lot of symmetries, and they had the classical state space that I was talking about, so they had at least 2,000 states as most, I think. And then they made simulations for a long time. I thought when I counted it, it would take a couple of weeks for one training in reality. And in other cases, they had one agent where it was just exploring its state space. It tried to find how to move around in the state space, but then they programmed it in before how to move in the state space, and it was just up to the reinforcement learner how to learn the probabilities. This had this underlying layer where it tried to figure out the body positions simultaneously. And in that case, they had to break the robot down in 3 different parts, where the torso was moving independently and the arms were moving independently. And in another case where they were using reinforcement learning, they had this little robot dog that was supposed to learn things it could do. It was the first paper, at least I read, when they were using curiosity-driven learning, but in that case, the actions it could do was really high level, so the actions it could do was pre-programmed, so it was like the robot is able to try to punch something. But no, I haven't seen, so far as I have seen, I think my method is faster than any other I have seen. But also, it's only limited because the robot will do things that are interesting within its state space of moving around. But yeah, but then you could do more work, like when it knows how to move around in the global space, when it can control that, then you could later use that as direct coordinates, because then it could control them more or less directly. I hope that answers some of your questions. Yeah. Yes?
So would it maybe be able to handle like some unstable states? So for example, if you learn to stand up, to stand on one leg?
Yeah, I guess if it depends. It would be helpful if the robot was able to get immediate feedback of what is the angle. Yeah. So because you can't wait here for 2 seconds before you conclude, no, I wasn't stable. So yeah, if you could do that faster, and but also you need to add more parameters. Perhaps it could be useful for the feet to be able to that instead of telling the feet to be in a special position, you can just tell the feet to be between those 2 angles and try to stay where the floor is. So if it stands like this, it would automatically go down like that to be more stable. Yeah. Because now it only has one angle to be in between. So yeah, I think there are a lot of spin-offs here, and. I was talking with my girlfriend. She reads to become a doctor, and she told that in our own bodies we have 2 different kind of states as well. We have the things that we are in direct control over. We can control how our body is within ourselves, in relation to ourselves, and also you have where is the body in comparison to the environment, and then the body tries to find how to use the ones their bodies in control with. So it's pretty similar to some features of our own body. And since our bodies are able to do that, I think that with the right kind of input and with the right amount of direct coordinates for the robot as well, it could be able to do more stuff. And since the posture is just a vector, it's fairly simple to just increase the length of it without making the problem more complicated.
I have one
Yes?
final question. What did you think was the most challenging part of this work that you have done?
It was, first of all, the abstraction to how can I handle this great state space? How can I, in some way, enable the robot to move, to try, how could I make the state space? In the beginning, I had the curiosity-driven learning algorithm. I knew that this is how I want my robot to train, and I also thought that reinforcement learning could be a good method, because in reinforcement learning, when you learn how to do something one time, then that knowledge will always be used. In other cases where you use like genetic algorithms, when you use evolution, then you have a slower evolvement. I wanted the robot to always, if it did something interesting, I wanted it to remember it immediately and be able to utilize it immediately. But then the problem was, how do I break down the state space? How can I make it less? And I think the idea of how to use the vectors came from the homeokinesis method I read about, where they were basically, they also did those kind of vectors, but what the robot then was doing was it was measuring how much, it was trying to find the gradient in how it was moving and try to always do the things that would increase the dynamic features of its movement. So it always tried to move the body with the gradient towards the most chaotic areas of its space. But that didn't work very well with humanoids, because humanoid robots lying on the ground, on the back, they are very stable in themselves. So there are no closed dynamic regions. The first problem was how can I abstract this to make the state space lot lesser. But the other one was to figure out how should the robot search for new states. How should the robot look for, it needs to find one posture for every state. How can I find the best one? So a lot of thought went into that, how to do it. And I only told you a simplified version now, but what I actually did was that I used a self-organizing map. Perhaps somewhat similar to cone and networks, if you're familiar with that, but still, it's completely different in some aspects, because it do something completely different. But the basic idea of a cone and network with nodes, with postures that are floating around in a larger space, and try to find some manifold. This is pretty technical, but you try to find some manifold in that space where the good postures are, because the robot can have so many postures, but we only want to find the relevant ones, the ones that make sense to the robot. The ones you try to find the embodiment of the robot. So to figure out how to do that was also pretty tricky. And more can be done on it, but it worked fairly well. And when I compared it to alternatives, it worked.